Hi everybody, and welcome to the CERIAS Security Seminar here at Purdue University. We made it through one more semester, so this is the last talk this semester. And it's my great pleasure to introduce David Pisano from MITRE. And he's going to talk about identity-based Internet Protocol Network. And he has a few other, I think, caveats here. The main idea is how to build it on existing equipment.
Yeah. Right. Well, good afternoon. I'm Dave Pisano. I'm from MITRE. I was actually a senior network engineer there. I'm also a contributor to the HoneyNet project. So identity-based Internet Protocol, or also referred to as IBIP for short. It's a project I've been working on at MITRE for about 2 years now. To sort of go over what this talk's going to cover, and to give you the the problems and the motivation behind this project. Go over the concepts of IBIP. I'm going to talk about some of the transformational security claims we're making with this, and go over the results of some testing we've done in the lab. So before I start, IBIP is still under development, so details are likely to change as things get implemented. And one thing I want to emphasize from the start is that IBIP is for enterprise. It's meant for enterprise networks and not the internet. With the current state of malware, it's impossible to prevent it from entering the network. There are numerous unknown vulnerabilities in software. With the current state of browser plugin security, and with drive-by web attacks, browsers are being compromised on a very regular basis, and also users will almost always be susceptible to social engineering and having their credentials stolen. Given the sophistication of current malware, host-based malware detection is a losing proposition. One of the first things that some pieces of malware do is disable the host-based malware detection. And sort of to give you a idea of the scale of the problem, something around 200,000 new pieces of malware detected every day. So what is IBIP? IBIP is a new network architecture that leverages the existing equipment in your network. We only need to add one appliance per layer 3 segment. This device enforces all behavioral and access control policies outside of the host system. Its key features are adding user and host identity into every IP packet while preventing spoofing. We add dynamic role and trust metrics that are used as a gating function for access control. Policies can be changed on the fly to adapt to the change in threat conditions of the network. Clients are hidden, and network infrastructure. Both clients and network infrastructure are hidden, except for authorized users and hosts. And any attempt to access these will generate an alert. IBIP allows for the creation and enforcement of permissible use policies for network applications. The major benefits to IBIP is that it combines both the user and host identity at the packet level, allows for the network to adapt to changes in the threat conditions, creates and enforces permissible use policies for the network and network applications, and how trustworthy users and hosts are. All of this gives the operator of the network unprecedented situational awareness and the potential for a truly self-defending network. The objective of actually IBIP was to test some recommendations put forth in a 2010 DARPA study that was performed. So let me go over the architecture here. The IBIP architectural concept involves making operational distinguishations between client servers and infrastructure devices, and between IBIP-enabled endpoints, either within a local enclave or outside through a trust gateway. IBIP policies are enforced at each edge point of the network, using quot switches and routers and a MITRE developed IBIP permissible enforcement point, or sorry, policy enforcement point, or PEP, which serves as the main policy enforcement point, and this is where we foresee this eventually being incorporated into commercial products. We refer to this concept of the switch PEP router as the IBIP edge string. Essentially, each end user is connected to the switch, and which is then backed. IBIP then backs each one of those by the PEP. Most of the IBIP architecture is built using COTS components. We developed the IBIP PEP, mentioned earlier, the registration server, and the network operations console. We're currently developing the trust gateway. The effect of the IBIP architecture is that access to the network is based on the user's identity and that of the machines. IP addresses are tied to this identity, and switches are configured so that each switch port is restricted to the host and user that authenticates, effectively eliminating the ability to spoof IP addresses. Private VLANs are leveraged to maintain separation between hosts on the same subnet. This combination of incorporating identity into the IP packet and prevention of spoofing provides accountability of traffic in a way that is simply not possible today. As mentioned previously, clients are hidden in the network, and what a client is permitted to access on the network is determined by the user's role and organization. Similarly, servers are constrained by policy to provide only those services that are authorized. If policies are violated, the network operation console is informed, and depending upon the current threat condition, those violations may result in a out-of-band or out-of-policy action being permitted, or so a permissible state which may appear as at a lower threat condition, so things might be allowed, or a denial state, and when a sort of restricted status of the network, or higher threat conditions, and for certain critical assets. The result of this is a network that is tailored to the business needs of those using it, with specifically reduced threat surface and improved network situational awareness. I'm going to go over sort of how the registration process and sort of some of the auto configuration stuff happens. So when a user or host connects to the network, they need to get authorized. To do this, we leverage 82.1x on the edge switch. So the system connects. It provides some type of cryptographically sound information. That information gets passed to the switch. The switch passes on to the registration server, which is just running a radius service. The supplicant on the host will first send some the hardware certificate information. This will create a encrypted tunnel between the host and the registration server. And then some certificates from a smart card or or other type of device will then carry the user information across. If a user is successful in authenticating, this process will then bind the physical port and the switch to the MAC address of the system. The registration server will auto-configure the PEP to bind the MAC address to the IP address of the system. If the host is serving as a server for both TCP UDP ports, usage policy would be pushed to only allow those authorized services. By requiring strong authentication to get onto the network, we're able to get accountability via a packet level ID that can be traced back to both the user and the host credentials. Through the MAC to port and the MAC to IP binding, we reduce the likelihood of spoofing and impersonation. With the registration server pushing source port restrictions, it enables it enables creation and enforcement of policies with a low false alarm rate. Also, all this together significantly improves the situational awareness on the network. So here's an example of how sort of the permissible use policies work and the effect that a violation has. So we have a web server here that is approved to run services on TCP ports 80 and 443. Any outbound packets coming from these ports are allowed through the PEP. If there's a packet from a port that is not approved, like from TCP port 23, it will generate a policy violation. This is then sent to the NetApps console with source attribution information. If the number of policy violations exceed a set threshold for either the user or host, trust metrics are then updated and sent to the registration server. The registration server then tells the PEP to update trust metric levels on the server's source shim on the ingress to the network, and you have the option of having a trouble ticket generated automatically as well. As I mentioned earlier in the previous slide, is a Shim. So this is sort of how IBIP is laid out for our IPv4 implementation. We have both this user and host identity that gets inserted into each packet. The Shim is both added and removed by the PEPs on each side of the network. The Shim contains attribution information for those sources, source and destination, and optionally the current role and trust levels of those systems. So, given the size of the size of our Shim, we can support up to about 1 trillion different IDs, about 32,000 organization affiliations, 212 roles, and about 8 trust levels. I'm now going to sort of explain how the Shim and access control is handled. Once the user is authenticated, policies are pushed to the PEP in front of them. This PEP adds shims to the outbound packet, and ingress filter policies are applied. The packet is then forwarded across the network. On the receiving end, the PEP applies egress filtering policies, removes the Shim, and then forwards the packet onto its destination. So I'm now going to start covering some of the security benefits of IBIP. So here's just a list of some of the current threats that sort of every network network today faces. So you got the typical insider threats, malware, compromised systems, supply chain threats, sort of anonymous operations, so the ability to impersonate or spoof someone else, vulnerable software, slow response time to patches, 0 days, human error, and a lot. And so this is what IBIP has to bring to the table to help either reduce or address some of those threats and vulnerabilities. IBIP allows for the policy to say that what should be permitted and by whom, even potentially by when and from what system. IBIP provides attribution accountability at the network layer. And this is down to both the user and host, and by making identity spoofing very difficult and failure attempts visible. This increases confidence in your information. By making clients and infrastructure devices inaccessible, this reduces the threat surface of your network. IBIP sort of establishes policy monitoring and enforcement external to the host. This separates the protection from the host so that malicious exploits that overrun the device do not also overrun your network protection. IBIP establishes a mechanism to dynamically adjust both roles and privileges of the user and host in response to triggered events. IBIP supports the concept of dynamic trust metrics. This can be leveraged as an additional discriminator in determining whether access to a highly sensitive material system should be granted to a particular user and host under different threat conditions. IBIP permits significantly enhanced situational understanding, both in real time and historically. This is enabled with the ability to do database searches for under-the-radar activity, but still have the information to attribute this stuff back to the host and user identity of the system at the time that activity happened. And this is accomplished because the identity information remains with the packet, and you do not need to depend upon log files for this identity information, which might have been rolled over or removed or deleted months or years ago. And so I've made some pretty bold claims here, and doesn't really mean anything unless we actually test this out. So to test these concepts, we had a penetration testing team come in. Prior to them coming in, they were fully briefed on how IBIP operated. We set up 5 objectives that they needed to accomplish. These were to gain access to the network, conduct network recon, spoof another an IP address, gain access to a server leveraging a zero-day exploit or a pre-placed backdoor, and try to gain access to a client from a server. The blue team role in all this was purely passive. They were not allowed to take any action on what they saw. If the penetration testing team could not accomplish an objective, they were given additional information to allow them to move on to the next objective. So during this, we had 4 simple policies in place. That all clients were hidden, infrastructure was inaccessible, each server had a permissible use policy. This was 1 policy per server and not a generic policy, as in the first 2 examples, or first 2 cases, and a minimum trust metric for ingress and egress was established. So we first asked the pentest team to try to just get on the network. We gave them access to a physical port and a Ethernet, so the MAC address of a valid system. We provided them a hub so they can sit in between a authenticated system and the switch. And we gave them, and they tried to use sort of unregistered or stolen credentials, or unregistered, stolen, or counterfeit user credentials to try to get on. they were unsuccessful in trying to access the network through these methods. Next, at this point, we gave them valid credentials and full access to the network so that they can now sort of try to conduct recon on the network. We gave them a list of all the IPs and MAC addresses used along with a network topology. Their objective was to verify the IP addresses of the client machines and any infrastructure designated systems. They also investigated if any eavesdropping was possible on active traffic between clients and servers on the switch. And so they do this, they use sort of basic tools, just mmap, ping, SSH, telnet, and something called the hacker's choice, which was a tool for doing things, getting additional information out of network traffic on local networks. And there was active traffic between both the clients and servers being generated while they were doing all this to try to do the eavesdropping. They were unsuccessful in performing any of these actions, and we caught them as they were trying to do scans of clients and infrastructure stuff. Next, they were asked to try to impersonate another device or spoof another device that was already authenticated. They first tried to send a packet with a fake source address. Next, they were provided with a MAC address and IP address of a validated system that was in use. They also tried this with a hub between the system and the switch. They were trying to impersonate, and again, they were unsuccessful in performing any of these or being able to achieve any of these objectives. So sort of next, we asked them to try to access a simulated zero-day vulnerability on a server from a fully compromised client. So give them a client, fully authenticated, can do anything that a client could do in the network. The target server was registered as a web server and was permitted to use ports 80 and 443. A telnet server was running on the system and port 23 to simulate a zero-day. Pen testing was provided the username and password for that server. They were also unsuccessful in trying to access that backdoor. So objective 5 was sort of, they had to repeat the same thing but try to access a client from a server. And they were allowed to install any software they wanted on the server they were using. But again, they were unable to communicate with a client. Over the course of them trying to achieve all these objectives, we were able to, as they were doing it, we were able to find out, or we were able to know what they were doing from the NetOps console, from the alerts we were receiving, and recreate it without any information from them. So just sort of summarize and recap. The benefits, and so by hiding the client systems, we reduce the threat surface by eliminating embedding user and host identity into every packet, and by preventing spoofing, we enable accountability and traceback of activity. By enabling access control based upon the user's host, both the user and host identity, we enable segmentation and isolation of critical infrastructure. By enabling permissible use policies for a network application, we are able to get increased situational awareness and understanding what is happening on the network. This is all implemented with minimal human interaction for infrastructure configuration. This leads to reduced chance of human error in any potential configuration changes. Any questions? Yeah.
So do you have a modified implementation of your TCP/IP? Because you drop in a new part in the packet,
Right.
And so that will change the error check.
Right. Because we drop it on the egress and then we pull it out on the egress. and as the error checking is done on the end systems, once it reaches the end system, the packet's back to the way it should be.
So you do not have any routers in the middle?
We do have routers in the middle, but the routers don't look at the overall checksums. So they'll look at sort of, the checksums they look at are the MAC level one. So
I mean, because you are
yeah, we stick, the header we stick between layers 3 and 4.
Oh.
So the routers don't care about 4 and up.
And so a follow-up was, so how was the system, the IBIP, right? Am I right?
IBIP,
Okay.
yeah.
Yeah. How is that system different from having an ALG and, let's say, an edge firewall? Because it looks like it does the same thing, but the additional advantage that you have is you're tagging every traffic to a user and to a host.
Right.
So there are two parts where you have a policy tagging as well as a hardware tagging. So
Right. So because we're tagging each packet and we're able to trace that back in the long run. That's an added benefit that you don't get out of existing systems. Yeah, some of the policy stuff you can do it on an IP and port basis with a standard firewall, but you have to put a standard firewall everywhere. But we can do more than just doing it on ports and IPs. We can leverage that identity information and do access control based upon that identity information, the role information, and the organizational information. And that's just something you can't do with a firewall, at least today. We also force, with the private VLANs, we force all the traffic to go through the policy enforcement point. So if I want to talk to a system that's sitting right next to me, I have to go up to the policy enforcement point and then come back. Yeah, it's not as efficient, but it's sort of a increased security over efficiency.
do you have any ALGs on the network with, because, before the end system?
Right.
Because when it's verifying the packet, it might find something odd.
No, we don't.
Yeah.
Not at this time. We don't have it. Yeah, and that is, yeah. If you have something in the middle that's actually looking at that information with the shim there, it has to know about that shim for it to work. Otherwise, it's just going to see it this is an unknown protocol. Either depending upon its configuration, drop it or let it pass, and it's not going to look like it. That is something that if something like this gets implemented on an enterprise network, your systems are going to have to be your systems that sit within the core and doing monitoring will have to be aware of that information exists.
And the tag was removed before the
tag is removed before exit.
Okay.
So
yeah, that makes it clear.
Yeah. So like if on your border, your tag will be removed before you exit the border to the internet. So your IPSs and stuff and firewalls there won't have a problem. But if you have like any IPSs in the core, yeah, right now, yeah, you'll have a problem. Down the road, if this sort of catches on and is commercialized and stuff like that, yeah, it will. Those things the devices will have to be aware of it.
I just have one more before I wind up. So is the inside host tagging it, or is it a device on the network that
It's the device in the network that tags it. So the hosts, we do no tagging on the host whatsoever because we don't trust the hosts.
Okay. Thank you.
Mm-hmm. Any other questions? Okay. Thank you.